In previous lecture, we talked about frequency response plot. Frequency response plot represent a completely complementary view of circuit. It basically describes how the circuit behaves as we apply different sinusoid with different frequencies in frequency domain. And we can describe this behavior as a relationship between the magnitude of h at j omega and omega itself. So this relationship describes the behavior of the circuit, and it is called frequency response plot. So here in this slide, I want to show you four major type of filter based on their frequency response plot. So based on how the relationship between omega and the magnitude of h at j omega looks like, we can divide our circuits, we can divide our frequency response plot into four main category. So the first one, in this lecture, I'm going to focus on ideal filters, and then we're going to talk about circuits that are very close to be estimated as one of these ideal filters. The first filter is low pass filter. So filter 1 is low pass filter. A low pass filter has a cutoff frequency, which I'm going to show it as omega c. And if the frequency of the input, so I have a system or circuit, and I'm applying a sinusoidal with a frequency, with a particular frequency, for example, a cosine of omega t. So if this frequency is smaller than omega c, then the magnitude of h at j omega is equal to 1, and if frequency is higher than omega c or cutoff frequency, then the magnitude of h at j omega is going to be equal to 0. So let me show that this omega c here is my cutoff frequency. So a behavior like this will be considered as a low pass filter. Any circuit that behave like this will be a low pass filter which has a pass band which can be described by frequencies smaller than cutoff frequency, and then after omega c will be considered as stop band. An ideal low pass filter can completely kill the input signal and make the output signal equal to 0 if omega is greater than omega c, or it can pass the signal completely without any drop in the magnitude, so a cosine of omega t, if frequency is smaller than omega c. That's what happens if we are looking at an ideal low pass filter with a sharp transition from pass band to stop band. The second ideal filter that I want to show you here is high pass filter. A high pass filter has a relationship which is exactly opposite of low pass filter. So we have a frequency which we call it as cutoff frequency, but what happened is exactly reverse of what happens with low pass filter. So if our frequencies are smaller than this cutoff frequency, then the magnitude of h at j omega is going to be exactly equal to 0 in an ideal high pass filter, and then after this frequency it's exactly equal to 1, and 1 means that the signal can be passed through this filter completely without any drop in the magnitude. Okay, so here we have the stop band, and here we have our pass band. So here the signal will go through. And same here. So here we have the low pass filter, and the signal will go through the circuit or the filter if input frequency is lower than omega c. The third type of filter that I want to show you here, in which we are going to work with this type of circuit later, is band pass filter. So the third ideal filter is band pass filter. A band pass filter can only pass signal which have frequencies between two cutoff frequency of the filter. So a band pass filter has two cutoff frequency, which I'm going to show them as by omega c1 and omega c2. Now, a band pass filter can pass the signal if the input frequency is between omega c1 and omega c2. Otherwise, it will completely damp the signal because the magnitude of h of j omega at those frequency smaller than omega c1 and greater than omega c2 is equal to 0. So it will completely kill the signal if the frequency of the input is out of this range of omega c1 to omega c2. So this is what we have as band pass filter, and the pass band is what we have in the middle. And the fourth ideal filter that you need to know about is band reject filter. Or it is also called a stop band filter. And in band reject filter, what will happen is, again, opposite of band pass filter. So still we have the same two cutoff frequency of omega c1 and omega c2, but this time frequencies smaller than omega c1 and greater than omega c2 can go through the circuit, but those frequencies between omega c1 and omega c2 cannot go through. So it will kill the signal if the frequency of the input sinusoid is between the cutoff frequency, and if it's out of this range, then it let the signal to go through the filter or the circuit. So here our band pass is frequencies smaller than omega c1 and greater than omega c2. So what you can see here and what we discussed about these four different type of filter are showing you the frequency response plot of ideal filters, but the circuit that you're going to work with are normally not ideal, so they don't behave they don't follow the exact same behavior. What you're going to see is something like this. So if you're working with a low pass filter, it will let the signal to go through if the frequency is very small, and for higher frequency it will kill the signal, but in the middle it's going to be something like this. So you cannot see that sharp transition between pass band and stop band. So something like this will be considered as a low pass filter. Or for high pass filter, your circuit will behave similar to ideal situation if the frequency is very high or very low, but in the middle you're not going to see this bold behavior. So what you're going to see as frequency response is something like this. So you're going to have some transition, but this transition is it's a lot more smoother than what you can see for an ideal high pass filter. Same thing for band pass and band reject filters. So what you're going to see is something in this form for band pass filter, and for band reject filter you're going to see something probably similar to this. So the goal of this chapter is learning how different circuits behave and try to describe their behavior as band pass, band reject, high pass or low pass filter. Now we can make these 4 different type of filter with passive or active element. So if we are using R, L, and C, only RLC component, then our circuit will be considered as a passive circuit. But if we are using active elements such as op-amp in our circuit plus RLC, then that circuit is active circuit, and so we have passive filter here, and here we are going to have active filter. What is the main difference? The main difference is that if you're having passive filter, it's impossible to amplify the gain. So what will happen is that if you input a signal, a sinusoidal signal with a magnitude of A, then what happens is that you're going to have a magnitude which is equal or smaller than the input magnitude. So your A prime cosine of omega t has a magnitude which can be equal or smaller than A. So there is no way that you can have amplification with passive filter, and that's why in previous filters all of them had a maximum gain equal to 1, that you can see them here. But if you are talking about active filter, because active filter, they do have some sort of source involved. When we are talking about op-amp circuit, the op-amp circuit has a power source. So because you have an external source in your filter, then you are able to see it's not necessarily a higher magnitude, but it is possible. So it is possible to have a gain here that is greater than your input gain. So the active filter can magnify, but the passive filter cannot magnify your input magnitude. The best case scenario is that it will let the signal to go through and keep its magnitude, and it doesn't drop the magnitude. That's the best case scenario. In next lecture, I'm going to show you how you can analyze a circuit and figure out if the circuit is behaving like a low pass filter, high pass filter, band pass filter, or band reject filter.